Hello everyone, my name is Javad and today I'll be presenting my project. It builds on the paper titled When Privacy Meets Security discussed earlier in our class. This paper introduced a method called the Ordered Markov Enumerator or OMEN for generating passwords using Markov models. My project takes a different approach by employing deep learning techniques, specifically transformer and language models, to create passwords. So the whole idea here is to generate passwords that have the most likelihood to be a human generated password. So when you feed this password into a cracker like Hashcat, it could be easier for you to crack your passwords. To download the Passform, please visit the provided GitHub link. There you'll find detailed sections about the project, including an overview, features, model architecture, installation guide, and etc. To install it, start by cloning the repository. Next, navigate to the directory and install the required dependencies. Once this is set up, you're ready to start. You can generate passwords by using the Python script called generatepasswords.py. This script allows you to specify the password length and the number of passwords you are wishing to have. Let's dive into the technical specifics of the Passform project. Start by opening the Jupyter Notebook to view the commands. The first command installs Optuna, a library for hyperparameter tuning, which is utilized in this project. Next, we import the necessary libraries. This model was trained using Google Colab, so the notebook is set up to connect to Google Drive. If you prefer to train the model locally, simply skip the Google Drive connection step and use the dataset available in the dataset folder. I've developed a class called Password Dataset, which is designed to handle the passwords we have in our text file. This class is responsible for opening a dataset file, reading each line, which represent a password, and cleaning up unwanted characters such as new line symbols, \n, for example, and other kind of white spaces. I've also overridden the methods like len and getItem to simplify interactions with the dataset. Additionally, we have implemented methods such as yield tokens and store-based parameters. Yield tokens add special tokens at the beginning and end of passwords, which is crucial during the training phase. The store-based parameters method is used for saving model parameters, allowing them to be easily loaded later into the model. Additionally, there are two utility functions, save vocab and load vocab, which are used for saving and loading the vocabulary respectively. We start by loading our dataset, which includes 16,000 unique passwords, and then split it into training, validation, and test sets. Next, we create our vocabulary, adding special tokens that facilitate training with the transformer model, and save this vocabulary for future use. The collate batch function is critical. It converts a batch of raw strings into batches of character indices, which is the format required for transformer models. This process includes masking, where we feed each password's character sequentially, trying to predict the next character to train the model efficiently. The batch size I use for training is 32, but if you have access to a more powerful GPU, you might consider increasing this to 64 or 128 to potentially improve performance and speed. Finally, we set up our data loaders and you will be able to see more metrics displayed on some static displays that provide insights into the training process. Now we start to define our model. First, we have the positional encoding class. This component provides information about token positions in the sequence. It calculates sinusoidal functions for positions, which are added to the token embeddings, enhancing the model's awareness of token order. Next is the transformer model class, which builds the actual transformer. It starts with token embeddings, applies positional encoding to embeddings, uses transformer encoder layers for processing. These layers handle self-attention and data transformation. The output of these layers is fed into a linear decoder to predict the next token probabilities. We initialize the weights to small random values to help the model learn efficiently. In summary, this setup embeds tokens, adjusts for positions, processes through encoded layers, and predicts outcomes, all using a standard components in PyTorch neural network library. In this section, we'll discuss hyperparameter tuning using the Optuna library. Optuna is an optimization library that automates the process of finding the best hyperparameters for your model. First, we set up the device to use for training. We use CUDA if available, otherwise, we fall back to the CPU. This is crucial for leveraging GPU acceleration, significantly speeding up the training process. Next, we define the objective function that Optuna will optimize. In this function, we specify the range and type of hyperparameters to tune. This includes the learning rate, the number of layers, and the dropout rate. We also choose from predefined configurations of model dimensions and attention heads. We initialize a transformer model with these parameters, then move the model to the appropriate device. For optimization, we use the Adam optimizer with a learning schedule that adjusts the learning rate over time. We train the model over multiple epochs using cross entropy as the loss function. During training, we pass data batches through the model, calculate loss, and update model weights. We also adjust the learning rate after each epoch based on our scheduler. Lastly, the model's performance is evaluated on a validation set to compute the average loss, which Optuna will attempt to minimize across trials. Finally, we set up an Optuna study to find the best hyperparameters. We configure the study to minimize our loss and allow it to run 20 trials in parallel, utilizing all available CPU cores to speed up the process. After the trials, we identify the best one and print its results. We display the minimum loss achieved. We list the hyperparameters that led to this best outcome, providing clear insights into which configurations work best for our model. To wrap up our optimization process, we retrieve the best hyperparameters identified by Optuna. We can either directly use these from the study or load them from a saved file. Using these optimal parameters, we reinitialize our transformer model. This includes the best learning rate, the optimal number of layers, the most effective dropout rate, and the ideal model dimensions and number of attention heads. Finally, we output the total number of parameters in this optimized model, providing a clear view of its complexity. We begin by initializing our model's optimizer and scheduler. The optimizer uses the Adam algorithm with a configurable learning rate, and the scheduler adjusts this rate after each epoch to improve training dynamics. We also set up the cross-entropy loss function for evaluating performance. In our training loop, we run epochs where each consists of a training phase followed by validation and testing phases. During training, we calculate losses and accuracies, update weights, and apply gradient clipping to stabilize the updates. In validation and testing, we assess performance without making adjustments to the model weights. We keep track of training, validation, and test losses and accuracies to monitor progress and perform early stopping if validation loss doesn't improve after several epochs. The best performing model, based on validation loss, is safe for later use. We use matplotlib to visualize our training process. The figure has two subplots. The first subplot displays the loss metrics. It plots training, validation, and test losses across epochs. The second subplot shows the accuracy metrics for training, validation, and test datasets, providing insights into the overall effectiveness of the model at each stage. The graphs shows the progression of our model's training over 100 epochs. On the left, we have the loss over epochs graph. It shows that all three datasets, training, validation, and test, display a decreasing trend in loss as the number of epochs increases, indicating good learning over time. The lines are close together, suggesting consistent performance across different datasets. On the right, the accuracy over epochs graph reveals a steady increase in accuracy over time for the training set. The validation and test accuracies also improve with some fluctuations, which is normal behavior. In this part of the code, we have two functions. The first function loads a pre-trained model and a vocabulary from a specified path. This setup is crucial for ensuring that we can reuse trained models with their corresponding vocabularies without retraining. The second function generates passwords using the loaded model and vocabulary. Here's how it works. We initialize the model in evaluation mode to prevent any changes during the generation process. For each password to generate, we start with a start of sequence token and iteratively predict the next character based on the model's output probabilities until we reach the desired password length. The generated sequence omits any end of sequence tokens, producing a final set of plausible passwords. This approach leverages the model's learned character probabilities to generate new data that aligns with the patterns seen during training. Thank you all for your attention. If there are any questions, I would be glad to address them now.